Hello everyone and welcome back to PC Retro Programmer, to this series on CGA graphics programming. In the previous video we introduced this algorithm here for drawing standard ellipses on the screen, and we implemented the first loop of this in assembly language. In this video I'm going to finish off this implementation, which actually won't require very much work. It's pretty much more of the same. In fact, the most interesting part of this will be the little correction in the middle of the algorithm. And then at the end of the video, I want to look at some much more interesting questions related to how we're going to do reflection for our ellipse. What we did with the circle won't quite work here, and we have some options that we need to look at. And it's an interesting question of which of these would be the best one to choose. So more about that towards the end of the video. I've zoomed this in a little bit more so that we can see the end of this algorithm, which is the bit that we're going to be working on today. Hopefully it was clear in the previous video that the variables x delta and y delta that I had corresponded to dx and dy in the actual code. I remember doing this because I thought there might be some confusion between the variable dx and the register dx. So I renamed everything to x delta and y delta, but then forgot to do it in the actual code. So I've caved in and gone back to just using dx and dy here. Anyway, what we need to do first is to code up this little bit in the middle that does the correction at the diagonal. So let's take a look at the code for that. Now the first thing that the code calls for us to do is to compare the variable d with dy divided by 2, or in other words dy shifted right by 1 bit. And of course we can do the shift right using our standard trick for doing a 24-bit shift, and this is just with a shift right and rotate through carry right instruction. But there's one problem here. The value dy is not necessarily even, so we can't guarantee that the bottom bit that gets shifted out is necessarily a 0. So when we do this shift, we might actually lose a bit at the bottom end of our 24-bit value. That'll get shifted out into the carry flag, and so somehow or other we need to preserve the carry flag. And there are various ways of doing this. You could push it onto the stack and pop it back off again to restore it. And there are instructions for that, push F and pop F. But this is pretty expensive. There's actually a cheaper way of doing it, and that's using the LAHF instruction. So this makes a copy of some of the flags, including the carry flag, into the AH register. And then to restore the value again later, we use its complement, the SAHF instruction, which takes those values back out of the AH register and puts them back in the flags and restores their values. And then we can undo the shift right with a shift left, making sure that we use the rotate through carry so that that bit that we shifted out gets shifted back in again. But everything else is pretty much the same as what we saw before. We have a 24-bit shift right by 1 bit, and we have a 24-bit comparison, and we saw how to do that in the previous video. And here we have a 24-bit shift left. The only difference here is that we're actually including the carry flag in the first part of that shift, because we want to shift that bit back into the bottom of the register. And that's essentially the if statement taken care of in the pseudocode on the left. Now the body of the if statement is pretty straightforward. We're just updating some values, and we already saw how to do this in the previous video, so I won't say very much about that. You can see that there's a label here, and this is because we're using our self-modifying code trick to write the value of the constant 2a into this constant here. And otherwise it's exactly the same as what we've seen before. And I actually added some lines above to actually write that value into this constant using self-modifying code. The rest is straightforward. Obviously we're updating our y value, and that's the same as updating our offset, and we've seen how to do this before in the circle and also previously in the code above for the ellipse. So that's the body of the if statement done. Of course we still need to deal with the case where the body isn't executed, where the condition was false, and in that case we jump down to here, And the only thing that we need to do in this case is just to undo that shift right by 1 bit that we did. And it's the same code as we had previously for that. We just restore the carry flag with the SAHF and then shift everything back to the left by 1 bit. So that deals fully with the entire if statement. And the next thing that it calls for is for us to negate the variable d. Now this is a 24-bit value, and so we need a sequence of assembly language instructions for negating a 24-bit value. Now machines store signed integers in 2's complement, and in 2's complement a negation is actually a complement, a logical complement of the bits. So replace zeros with ones and ones with zeros, and then add 1. So that's how you do a negation in 2's complement. And that's exactly what this assembly language instruction will do, but it's only going to work on 16 bits. So we call this for the low 16 bits of our value d, and it might be that after doing this complement and add 1, that there's a carry out of that. And this instruction actually puts that carry in the carry flag. And that means that we can continue our negation by dealing with the upper 8 bits ourselves. So we complement the upper 8 bits, that's the first thing, and then there could still be a carry that we need to add out of the negation here, and we add that to the upper 8 bits using an add with carry. And just add with carry with 0, of course. That's only the carry bit that we want to add. And so that completes the entire 24-bit negation. So this is how you do negation when you have a value that's bigger than a register. You do the bottom part using the negate instruction, and then you do the top part manually yourself, just making sure to add that carry on. So that's the end of the correction in the middle of our algorithm here. And the bottom part, I'm not actually even going to go through because it's pretty much identical to the top part. We don't really change very much in the code here. We're just updating some values. There's some if statements and loops and so on. And it's exactly the same as what we saw in the previous video. So there's no point going through this in any great detail. So that brings us to the end of the second part of our ellipse. This will be the next octant basically, and so we've now drawn an entire quarter of an ellipse. So let's take a look at what the result looks like. I already assembled and linked the code. This is in ellipse2.asm if you're following along at home. And so now we can just run the executable and see what it looks like. And you can see that we have a quarter of an ellipse on the screen. It's not circular yet because of course we didn't pick values for our semi-major and semi-minor radii that are in the ratio 6:5, but we'll do that eventually and we'll see that it will actually draw a circle. For now we have another question to start thinking about. How are we going to reflect all of this? You can see that if I reflect this about a vertical axis, I'll get the entire bottom half of the ellipse done, and then if I reflect all of that about the horizontal axis, then I'll get an entire ellipse. Now of course with CGA it's not going to be possible to use the exact same code and just make some small modification to it to get it to draw both the left and the right half of the ellipse. That's not possible because of the way the pixels are stored in the bytes in video RAM. As I am shifting everything to the right by 1 pixel on the right hand side of the ellipse, I'd be shifting stuff to the left by 1 pixel on the other side of the ellipse, and that's just going to be impossible to do without adding a lot of additional code, and of course we've completely run out of registers at this point, so it's not going to work. So we're going to have to run a version of this code that's just modified to draw the left-hand side of the ellipse. It's exactly the same code, it's just that every time we would move right, we move left instead. And I'm sure that you can imagine exactly what this code looks like, so I'm not going to go through that in any detail. The much more interesting question is how to deal with the vertical reflection, because that is something that you could imagine doing by just making a small modification to our existing code. Now, the way that we handled this in the case of the circle was to set aside a register in the CPU to hold the offset of the pixels on the reflected part of the ellipse. So every time we draw a pixel on our ellipse, we then switch over those offsets and draw the corresponding pixel on the reflected portion, and then switch the offsets back again for the next pixel, and so on. Now, this is a nice trick if you can use it, but it's not going to work here for one simple reason. We're out of registers. Those 24-bit values that we had to store use so many registers that we've got nothing left. Now, we could try and skimp and save somehow and find a way to save enough space so that we've got a spare register, but I really don't see a way to do that in this ellipse code. One way that sometimes works is to look at where the values need to actually be stored in registers, and sometimes you'll find that a register really only needs to be used for, say, half of the loop, and in the other half of the loop it could have any value in it. And so basically you can use that register for a different purpose in that part of the code. But I don't see a way that we can make that work here, and so I really think we are actually out of registers. Now, another approach that's more interesting that we could explore is to not draw our points directly onto the screen, but instead just compute their coordinates and store those coordinates in an array in memory. And then later we have a separate piece of code which reads those coordinates and draws the actual points on the screen. So by splitting up the computation of the coordinates from the actual drawing code into two separate pieces of code, we could hopefully use fewer registers in each portion of the code. And hopefully that means that we can keep everything in registers. Now, of course, there's an additional cost to writing out the coordinates into memory and reading them back in again, but actually this cost is not that high compared with the cost of actually computing the points and actually drawing the points. So it turns out that's not as bad as you might expect. And there are other advantages to doing things this way. If we've got a piece of code that can write out the coordinates of points on an ellipse, we could use those same coordinates for drawing filled ellipses, for example. All we really need is the coordinate of a point on the left-hand side of the ellipse and the coordinate of the corresponding right-hand side, and then we just fill in all the points between on that scan line, do the same thing for every scan line of the ellipse, and we have a filled ellipse. So this is actually an approach that we might explore in a later video for comparison. But the approach that we're going to take is a little bit different. It's a very standard approach when you run out of registers. We're going to use a memory variable instead of an extra register. So it's as though you had an additional register, it's just a little bit more expensive to access it because you have to do writes to memory and reads from memory. Now, ordinarily you want to avoid doing this at all costs because reading and writing to memory is expensive. But in this case, it's going to save us so much that it's actually worth doing. Because the only other way we could handle this is to compute all the points for the bottom half of the ellipse and draw them on the screen, and then do pretty much exactly the same computation again all over, and then draw the points on the upper half of the ellipse. So we'd be duplicating all that computation code, which is really expensive. So what we're going to do is do the computation once for the bottom half of the ellipse, and then suffer this tiny additional extra cost to keep track of the offset for the reflection in a memory variable, and that'll enable us to draw both the point on the ellipse and its reflection all in one go with this tiny additional cost. So that's the approach we're going to explore in the next video.